So welcome back to our latest lecture session. So again, as is customary, we are going to look at or have a brief summary of what we discussed in the last class. So I believe you are talking about or discussed in greater detail with respect to applications of VMINTEQ or visual MINTEQ to be able to predict your titrations. Yes. So that's something that's going to help you in cutting down on your time. Yes. And then we started talking about briefly about buffers. So let's look at where we are. So we have been talking about titrations, right? And we came up with calculating the relevant equivalence point, and that I believe was equal to 0.5 pKa minus log total base or weak acid present. This is something that we derived, right? I think this we derived when we had a weak acid or its conjugate base titrated against a known concentration of a strong acid. So for this particular case we derived this. So from here we can clearly see that the pH of the equivalence point is going to be near the pKa, right, or more or less half of the pKa minus log Bt, but because it's logarithm of the total base, right. So the effect of the concentration of the total base might be relatively less, but the pKa is going to be the major factor. So that's what you see here, right. And again, what is this equivalence point? That's when the amount of acid added is equivalent to the amount of base present initially in the solution. So in effect, what does this mean? So we have some base here in our solution. We know what the base is, right? That's why we have the pKa value or of that particular base or the weak acid, pardon me, weak acid or base, you know. So again, we have the we know the base, but we do not know the concentration. So what are we trying to do? We are trying to titrate it with a known concentration of a strong acid. So what is it that you are trying to achieve here? You are trying to see to it that you are going to consume all your base, right, by titrating it with your acid. Yes. So once you reach that particular equivalence point, what does that mean? So the amount of acid that you titrated with or titrated, I guess, right, or consumed is going to be equal to the amount of base that's initially present. So then by stoichiometry you can obviously calculate what's the concentration of the base that's present in your particular solution. So that's with respect to titration, and then we moved on to looking at VMINTEQ, right, and looked at titration and also the sweep menu, right, where you can change one parameter, which in that case was pH. But again, the titration menu would be much more helpful. When is it now? When you are going to look at, let's say, a complex titrant. Let's say when you have more than one constituent in your burette, right. In the previous example we looked at, we just had an acid, but let's say instead of an acid we had other constituents, let's say other cations or anions, which you are titrating against our particular solution. Then your particular titration menu is going to be much more helpful, right. So we are done with that, and then we moved on to buffers, right. And buffers, what's its role, or why are we trying to look at buffers? Because when we have a buffer in the system, they can resist the change in pH in either direction. Either you know, decrease in pH or increase in pH, they are going to resist the change in pH, but obviously at not all the pH values, at a particular set of pH values, depending upon the kind of buffer you use. Anyway, we are going to discuss that in greater detail, but in general, buffer, again, what are we trying to look at, or what do we need to understand? We need to understand that a buffer can resist the change in pH when you add either an acid or a base, right. The key is either you add an acid or a base. And in that particular context, we went ahead and looked at a particular graph, right, when we looked at addition of an acid and addition of a base and try to identify those regions where you know, the buffer capacity is high or the solution acts as a good buffer, and also those ranges of pH where the solution would not act as a good buffer. So I believe we looked at a generic example, but for purpose of you know, understanding the system better, let's try to again go back to VMINTEQ and use titration, and then let's see, you know, with respect to acetic acid. Acetic acid is something that we have as an example used widely in the previous lecture sessions, right, or frequently, pardon me. So we are going to look at that particular example. Anyway, let's look at the example here. So we are going to look at buffer or I am going to identify those regions where the solution which has acetic acid, right, where it's going to behave as a good buffer, let's say, or it's going to give a good buffer, I guess is a misnomer. I shouldn't use the term good buffer. I should have said buffer intensity, where the buffer intensity is relatively higher, right. So we are going to look at that particular aspect. So let's go back to our VMINTEQ here, right, and let me see that I'm going to have addition of a particular, let me see, okay, I don't have anything here. Back to main menu. So I'm going to start with acetic acid. So what do I need to have? H, right, and let me go with acetic acid and 0.01 molar, add to the list, and again acetate, right, and I need to add the organic compounds, which I believe I did, same concentration, right. Let me view and edit the list, 0.01 and 0.01. So I'm going to go back to the main menu. So what is it I'm trying to achieve here? I'm trying to see to it that, so what am I trying to achieve here? I'm trying to see to it that I get a graph where I have pH here, and then when I add an acid or a base here in the first case, how is my system going to change? And then when I add an acid, again, how is my system going to change? And the example I am going to look at is acetic acid. And we know that the pKa of acetic acid is what now? I think 4.76 or 4.75. Anyway, VMINTEQ should take care of that, right? And so now we are going to try to develop this graph. For this example, I am going to assume that the initial concentration of the acetic acid, HAC or CH3COOH that I am putting into the system is going to be 10 to the power of minus 2 molar or 0.01 molar, right? So again, what's the example we are going to look at? That initially we are going to have HAC naught is equal to 0.01 molar, right? And then I am going to set up the system such that I am going to titrate with an acid, right? And in this context, I am going to obviously set that the H plus concentration changes. So again, back to VMINTEQ here. So we already added the relevant components, but now we need to look at the titration mechanism here. So here the number of titration steps, let's say I am going to have 50 to be able to capture a wide range of pH, and then pH is the only output that I am looking for. I am not looking at the concentration of the other aspects or the other variables like acetate or the protonated form of acetate and so on. So then going on to the titration manager, I am going to choose a huge volume of the solution to be titrated. Why is that? Because I want to see to it that the concentration of this particular the constituents in this particular solution do not change. Again, I believe this is something we discussed in one of the classes recently. So think of this, why are we having a, or setting up the system in such a way that we have 10,000 of these units now, of the solution. Why is that? So let's say if I just took 100 and I added 20 ml or 20 units of my titrant, the total volume is going to be 120, the concentrations are going to change. So to get around that, what are we trying to do? We are going to create a hypothetical situation, or look at a hypothetical situation, pardon me, when we have a huge volume, right? In this case 10,000 units, and I am going to titrate it with, let's say 20, or in this case 50 times with 1 unit each. So 10,000 and 50 doesn't make much difference in the concentrations of the relevant components. But obviously for this to be achieved, or for my objective to be achieved, which is changing pH, I need to increase the concentration of the acid or the base that I am putting in, right? So again, let's come back to the system. So here I am having a huge volume, and then I have, let's say, volume of titrant to be 1, so in 1 unit, and it's only going to start at the second step because I want to know what the initial concentration is going to be, right? And then I'm going to add a base because I know that initially the pH is going to be less because I put in acetic acid. So where is the base here? Okay. So and here the base, because the base I need to add a negative value here, right? So it's going to be -3, let's say. That's something I believe I looked at for trial and error earlier. So let's save that. So what does this mean? I am adding 3 moles per liter of a base. Minus indicates that it's a base. but obviously the components in VMINTEQ only have H plus, right, not OH minus. So again save and back to multi-sweep menu, and here 50 steps, so 50 steps of 1 unit each of the titrant, and pH is going to be my output. So save and back, and I am going to run the VMINTEQ, right. And obviously the first case we can look at is, because I am just adding HAC, obviously the pH is going to be in the acidic region 3.38, and the number of titrations here are 50, as you can see, or iterations, pardon me. And then I need to look at the selected sweep results. So, and I see that with my increasing base concentration, problem 1 means 0 base added, and minus 3 molar at 1 unit concentration is added at problem 2, and so on and so forth until we reach 50 units, I guess. So as we see, the pH is initially less or acidic, and then as we keep adding the base, you see that the concentration keeps increasing, and then we end up with the concentration in the basic region. So here keep in mind that the final pH is 11.6. Why? Because when we look at the titration with respect to the acid, we are going to try to start from this particular pH. Anyway, so what can I do? I can print this to Excel, and I guess it's somewhere out here, and here we have the relevant data, right. So I am going to close this because I saved what it is that I did earlier. We are going to come back to that later, right. And so again, let's look at what we just have. Let's come back to our slide. So for now we have a particular data where we have pH and amount of base added, right. So initial base pH was around 3.8, and this base was 0. So 1, 2, 3, 4 and 5 until 50, and I believe we ended up with a pH of 11.6 or 7, right. So now I am going to choose a second case where I am going to add acid, amount of acid added, right. But now I am going to start from 11.7 or 11.9, I believe, and then I am going to look at the decrease in pH, right, so that I can have a relevant graph. So let's go back to VMINTEQ and look at how to go about it, right. So I am going to come back here, and I am going to edit my list, obviously, right, and acetate I am going to keep that as same, but to be able to come up with a higher pH value, right. So now my initial pH should be around 11.7. So I am going to say that I added NaOH and also NaAC, right. NaAC is a base, conjugate base, so the pH will be relatively basic, but it will probably not be, or certainly not be, as high as what is it now, 11.7. So I am also going to add some NaOH to be able to take the pH to around 11.7, right. So let's go with one trial. So let's see what we have here. So H needs to be negative, obviously, so we are going to go back to the key here, and minus. So this means I am adding a base NaOH, and this is the NaAC. So I am adding NaOH and NaAC, right. So back to main menu, and obviously I need to add the sodium, and let's look at where that is, GKLM right, and here we are going to have it as 0.02. So add to the list. So again, what does this mean? We are initially adding NaAC and NaOH, right. So that's the case how we are ending up with this particular case, right. Anyway, in case people are confused, let's go back to the slide and come back to. So what are we adding here? Earlier we were adding HAC naught initially, but to be able to start with a pH near 11.7, we are now adding NaAC base and also NaOH, right. So that's why the acetate total is going to be equal to the NaAC added initially, and H total is going to be equal to the negative concentration of NaOH added initially, and this is from the background that we have had in the previous classes. And obviously Na total is going to be equal to the sum of NaAC added initially and NaOH added initially. So this is the trial I am going with. So let's go back to where we are, list of components. So this is the relevant components here, or these are the relevant components here. Back to main menu and multi problem and sweep. So I am going to still stick with 50 titration steps, and I am still only going to look at pH. But in the titration manager, where earlier we added a base, right, that's what -3 indicates, we need to add a acid now. So to be able to have a comparable graph, I am going to keep the concentration of acid the same and all the other units the same, right. So I am going to delete this component, again go back to finding H, right, and then I am going to say that it's going to be equal to the same concentration of the base that was added earlier. So save and next, save and back to multi-sweep menu, and save and back, and now I am going to run the VMINTEQ. So obviously the first case that we see is we end up with a pH of 11.9. So 11.9 is a bit higher than 11.7, which is what we were aiming for, but to save time we are going to go ahead and look at this particular step for trial and error, right. And so then we are going to look at the circuit sweep results. So initial pH was high because we had NaOH and NaAC in our system, and then we end up what do we see, adding the acid, and obviously as you see the pH decreased, and it decreased till around 4 or so, right. So that's what we have here. Again I am going to print this to Excel and so on, but to save time I already saved the relevant data in an Excel sheet. So let's look at what I have. So here I have the titration step here, 1, 2 and so on. In the first case we have the case where we added the base, these are the results. So we see that the pH increased, and in the second case I have acid added, right, that is why we see that the pH is decreasing. And then I plotted this here in this particular graph, and we see pH on the y axis and acid or base added on the x axis. So let us see, the blue color legend is for the base added. So we started around pH 3, that is what we see here, or 3.3, and we start adding the base and we see that the pH increased, right, that is what we see here. And with respect to the acid, we started at around pH 11.9, right, and then started adding the acid in equivalent quantities, and we see that the pH obviously decreased to around I believe 4, I guess 4.2. So now we are going to try and understand this graph, right. This is similar to what we looked at earlier, but keep in mind that we are looking at a specific example here when we had acetic acid or acetate in the solution at the relatively similar concentration, which what is it now, 10 power minus 2 molar, right. So in one case we looked at adding the base from a lower pH to take the system from lower pH to higher pH. The other case we looked at bringing down the pH from around 11.9 to around 4 or 4, I guess, right. So that is what we are looking at. And what is the point of this particular exercise? We are trying to identify those zones in the particular system where if you have acetic acid present, will you have good buffer capacity, right, or buffer intensity. So we are going to look at that, let us see. So obviously we are going to look at those zones where the pH changes relatively less, right, the change in pH should be relatively less with the change in acid or base added. So right, obviously as you can see, what does that mean? That means that whenever the slope is less or when it is less steep, that means the change in pH, for example if I look at this region, let us say, it means that in this particular region you need to add a lot of base or lot of acid, right. So if you look at this particular region, we need to see that to go from pH around 12 to let us say pH around let us say 11, let us go with 11. So let us say 11 is here, I need to add almost 20 units of that particular 3 moles per liter of acid. And same case here, to go from pH of around 4 to pH of around 5, let us say, I need to add around 20 units of this particular base, right. So what does that mean? For a small change in pH, a large amount of acid or base is required. So the system acts as a good buffer in this particular region, right. So coming back to this region there, what do you see? You see that the slope is very steep here, right. So what does that mean? For a small change in pH, as in or for even with an addition of a small acid or base. So let us look at this particular region, right. What do we see? Even with a few quantities, let us say 5 units of the acid or base added, the pH is changing from 10 to 6 or again going from 6 to 10. So in this particular region we see that the system acts as a very poor buffer, right. Again, obviously at the higher pH, when because it's logarithmic scale, as you go to the extremes, to change it you need to add a lot of base or a lot of acid. So again you will see that the system acts as a buffer or good buffer at the extreme pH values. So again, what do we see around pH 4.76? We see considerable, what do we say, buffer capacity. So we are going to come back to this. So keep in mind that we are looking for small changes in pH even when considerable quantities of acid or base are added. So that's when you say your system is, your buffer is worthwhile for you to be able to use at that particular range of pH. So for example, here the take home messages are that, let's say just because you have a buffer doesn't mean it's going to resist the change in pH at all the pH, right. So you see that there are only a particular ranges, within which your particular buffer, in this case acetic acid and acetate, are going to act as good buffers, right. So that's the key here. So there are only specific ranges, so we are going to try to identify what these ranges are and so on and so forth. Yes. So let's move back to our system here. So we looked at this particular graph and we were done with looking at buffer, right. So examples of good buffer, what are they? I guess examples of good buffer, how can you identify them? You can identify by looking at the pH versus the pH versus acid or base added graphs, right. And you see that the flat regions, right, what does that mean? When there is a small change in pH with change in either acid or base addition, dpH by dt, right, that's dHT, pardon me. So again, what does that mean? That means small change in pH when large amounts of acid or base are added, right. This is what we see. So in this particular flat regions, we see that the system is a good buffer. So obviously, conversely, what does that mean? When we have steep portions or steep change in pH, steep change in slope, pardon me, or high slope, dpH by dHT, right. So in those cases, we see that the system acts as a poor buffer, right. So again, H total, not H, because this is some mistake that people make, thinking that it's a change in pH with change in H plus. No. Why is that? Because H total takes into account both the acid and the base added, but H plus takes into account only the acid added. So right, when we are looking at change in pH, when resisting the change in pH when either the acid or the base is added. So thus we need to look at that particular aspect, which is H total here, right, dpH by dHT. So now we are going to try to quantify what it is that we are up to, right. Again, you don't or never need to mug up these derivations or such, same case with the equivalence point derivation or any other derivations we looked at. The objective is to be able to understand the basics or fundamentals behind what we observe or the equations that you typically end up using, because in general they are bound by some assumptions, and obviously when those assumptions are not valid, your equations are invalid too. So in general though, whenever we look at or we try to use equations or such blindly, or especially the derived equations, without having an understanding about the underlying derivation, it's not fruitful in the long term to end up just mugging up those equations. So again, you don't need to mug up the derivations, but you need to have a understanding of what we are looking at, right. So let's go back to where we are. So now we are going to look at a new particular term that's called the buffer intensity, right. So beta is what we are going to use it. So what is this, how can you define that? Let's say, obviously how can you quantify that? So we are looking at trying to bring a relationship with the change in pH whenever H total is added, right. And you know that when the region is flat or when the slope is less, the buffer intensity is high, and when the slope is high or the steep slope, the buffer intensity is less. So obviously it's inversely proportional there. So minus 1 by the slope, which is d pH by dH total, right. So this is what we have. This is the buffer intensity, and that's going to be equal to minus dH total by d pH, right. So people might look at this, but keep in mind this is the source of your particular buffer intensity. So in the next set of slides, or over the few minutes, we are going to try to calculate this particular buffer intensity. Again, why is this buffer intensity useful though, right? Let's say you are trying to or this is your engineered system, and you want to add a particular acid or a base or conjugate acid base system to be able to resist the change in pH. So how do you know how much amount of acid or base is it that you are going to add? For that, you are going to need buffer intensity, right? You will first need to be able to estimate what is the allowable range of pH that you are fine with, as in, are you okay with the pH? Let's say if you are trying to maintain your system at pH 7, are you okay with the system swinging from 6 to 8, or do you want to have a very highly buffered solution where you are only fine with change from 6.9 to 7.1. So obviously if you are okay with, or if you can live with a pH change from 6 to 8, right, you will need to have a remarkably high buffer intensity. And if a low buffer intensity, right. Again, if you are okay with a high pH change, so that means your buffer intensity can be less. But if you are not fine with it, if you want to be able to maintain your system within a narrow range, and in this specific example, let's say 6.9 to 7.1, you obviously need a high buffer intensity, right. So in the next session, we are going to look at this particular derivation with respect to buffer intensity, and we are going to try to link that to the relevant aspects that we know. What are they now? Obviously we know that it's going to be relevant to pKa, right, certainly pKa, and also the amount of base, or this total base that's present in your solution. So we are going to first apply that to a monoprotic acid and then to a diprotic acid and look at the relevant aspects there. And I guess we are running out of time. So with that, I'll end today's session, and we'll continue the other aspects in the next session. Thank you.